Good afternoon to one and all. And today concept is about global optimization. And in that global optimization, I'm going to discuss about the data flow analysis and how to implement the data flow analysis in global optimization. And today concept is global optimization. In the last classes, I explained about the local optimization, right? Right. So in today's class, I'm going to explain about the global optimization. And once I'm recalling that what the local optimization is, and the local optimization is having a restricted scope. What it means is for only certain specific blocks we are applying the local optimization techniques. But while coming to global optimization, it is a broad scope. And here, throughout the whole program, we are going to apply the optimization techniques of global optimization, and also within the procedures of the program, we are going to apply the local optimizations. And what the difference between the global and the local is, here in the local optimization, it is a very restricted scope, and while coming to the global optimization, it is a broad scope. And that's the main difference between the local optimization and the global optimization. And here, today's topic is about global optimization. And in this global optimization, a program is represented in the form of an program flow graph. It's represented in the form of a program flow graph. That means the program flow graph is a graphical representation in which each node represents, and we all know how to represent the basic blocks and how to represent the flow graphs from the basic blocks. And we all know what the edges of the flow graph is. And here also, again, I'm recalling that the basic blocks and the edges represents the flow of control from one block to another block. That we are calling it as an flow graph. That we are naming it as a control flow graph, right? And see here, this is the structure of the data flow analysis. That means it is a structure of global optimization. And here, from the source code, from the source code, the source code is parsed to produce an abstract syntax trees. And these abstract syntax trees are used when those are transformed to the control flow graphs. And here, the data flow analysis operates on the control flow graph and any other intermediate representations. Then we are generating an object code. I think you all understand now by seeing the structure. It can be called as a conceptual view. Conceptual view of global optimization. And initially with the source code, and then it is for then we are producing the abstract syntax trees. And by taking the abstract syntax trees, we are transforming that syntax tree into a flow graph. And there at the on the flow graphs, on the control flow graphs, we are operating by using the data flow analysis, and finally we are generating an object code, that is a target code, which is an efficient target code, machine dependent code. And here not only the control flow graphs, we can also take the intermediate representations as an input when we are representing the or when we are implementing the data flow analysis in global optimization. And here what is an abstract syntax tree? What is an abstract syntax tree? And this concept I already explained at the intermediate code generation phase. They were having a concept like in forms of intermediate code. This is an first initial form of intermediate code that we can name it as an abstract syntax tree. And this is the natural hierarchical structure, and it is represented by the syntax tree. And here a DAG, that is a directed acyclic graph, is very much similar to the syntax trees, but there are some more compact forms. It means they are in some more compact forms while compared to the syntax trees. And here, whatever the code that is being generated as an intermediate should be the representation of the, either it may be in the form of a syntax tree or it may be in the form of a tag representations. What it means is, from the output of the intermediate code, I need to implement like in code optimization, right? And there at the intermediate code, what the output is generated there, my output is in the form of an intermediate language, and that is acting as an input to the code optimization, right? So whatever the code that is being generated as intermediate should be such that the remaining processing of the subsequent phases should be easy. Make it clear. That's why we're implementing all these phases to make it easier, to make it simple at phase by phase level. We're optimizing all these things by performing the transformations or by applying the techniques like this. And once you all of you see the slide here, the slide consisting of an example where the name of that example is and it is an abstract syntax tree example. And here the source code is x is equal to a plus b, y is equal to a into b, while y greater than a and a is equal to a plus 1, x is equal to a plus b. And what the meaning of this code is, and here it is a combination, the code consisting of three address statements. And with the three address statements, I am implementing an abstract syntax tree, and here I'm having some rules to be followed. What the rules are: my interior node should be the operators and the exterior node should be an operands. What it means is the plus star greater than equal to assignment operator, all these are all the operators, right? Those are all comes under the interior nodes. It may be a root node or it may be a child node. But whatever the leaves I'm going to generate, those should be the variables. What the variables means here, those can be called as an operands. That means a, b, x, y, like that. As from the given code, x, y, a, b are the operands here, right? And this is the way of representing an abstract syntax tree from the given source code, and my source code is in the form of an intermediate code. And here, what the abstract syntax trees are. These are an abstract, a kind of abstract. What the kind of abstract means, they don't contain all the information in the program. For example, if the source code consisting of any comments or brackets or parentheses or spacing, we are not considering all those. Without those, we are representing the tree structure. And we can easily resolve the ambiguities. How we can easily resolve the ambiguities means, for example, we're having expression c a plus b plus c, whatever the tree, what the tree that it produces means, if we're having an expression like open parenthesis a plus b closing parenthesis plus c, and if you represent for these two expressions, it looks similar because there is no difference. For the parenthesis, we are not representing as a node. Either it can be parentheses or spacings or comments. We are not considering them as an nodes. So always have my interior node should be an operators and my exterior node should be an operands. So by only considering the operators and the operands from the given expression, and here I am representing the trees for the both examples. But at last, when I look those two structures, they look very similar. They look similar. There is no difference between those two. That's in such a way I can resolve the ambiguity just by using this abstract syntax trees. And what next is, what the disadvantages of this abstract syntax tree? And here we're having some of the disadvantages of abstract syntax trees. What are those means? They have similar forms. While we are constructing the trees for while or repeat or until or if condition or switch case. For example, if we consider all these control statements or the conditional statements, when we represent an abstract syntax trees for these, it may look similar. They are all in similar form. So the expressions in the abstract syntax trees may be complex, and we can also form the nested loops. And so, for example, here we're having an example. If you see the example, by seeing the example itself, we can say the expression itself it is in complex. When we are representing an abstract syntax tree, the representation may be complex. So here we are also forming the nested loops as from the given example. And also these abstract syntaxes want the similar representations for the analysis. And here what the analysis we are implementing is, it is a data flow analysis, right? So at last, sorry, at least for data flow analysis, there are similar, we want the similar representations for the tree representations like an syntax tree representations. And what the next is, after knowing what the abstract syntax tree and how to represent the abstract syntax tree from the source code and knowing about the disadvantages, and then going to know about what the control flow graph is. This concept was already explained in the last classes what the control flow graph is. And here first initially you need to know what the flow graph is, and the definition of the flow graph was already explained, but again I'm recalling the definition. One, see, it is a directed graph. A flow graph is an directed graph. And here each node represents a statement, and the so block to block we are having the arrow representation, right? What the arrow representation is, and it is an edge representation. The edges represents the control flow. It shows the flow of control from block to block. And here what the statements means, the statements may be in assignment statements or copy statements or conditional or unconditional statements, etc. But here we're only considering the three most important statements. One is an assignment and one is an copy and another one is an conditional or unconditional statements. And here we're calling them as an jumps, conditional jump and unconditional jumps. By using the go to L, we are using the conditional jump or the unconditional jump here. And what the assignment statement is, for example, if we are having x is equal to y of z, and this is an expression, this is an intermediate representation of the language construct for the assignment statement. How we can represent is either it may be x is equal to y of z or x is equal to of z. And if we are having the copy statements, and how we will represent the intermediate language for the copy statement. And here, for example, my language construct consisting of some copy statements. So for those language constructs, I am using the copy statement in an intermediate language as x is equal to y, and branches go to L, or if relational operator, any type of a relational operator, it may be less than, greater than, less than or equal to, greater than or equal to, or not equal to, or equal to, whatever it may be. If a relational operator with the variable like an x or y, whatever it may be, then go to L. L is a leader here, or label, we can consider it as an L is a label, and so on. And these are the some of the rules that we are having for representing the flow graphs. We need to follow all these, right? And see here, this is an example for the control flow graph. For the same source code, here I am representing the control flow graph. See, there is a control flow from block to block, from statement to statement. We are having the flow of control just by representing like this. It can shown. See, here I am forming the loop. Why I am forming this loop means here we are having a while condition here. While condition, that means go to the label, which label it is, and it may be a label 3. Go to label 3. If the condition x is equal to a plus b, the computation of the line statement x is equal to a plus b was computed, then go to y greater than a. That is an L3. This is an conditional or unconditional jump here we are using. That means with the loop like this, by forming the loop like this, we are showing that. These are all called as an edges. These are all called as an edges. And this is a statement. All these are the assignment statements because those are all in the form of an x is equal to y of z, x is equal to y of z. And this is an if 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 relope y, anything and relational we are having, go to L. And this is again an assignment statement, and this is again an assignment statement, right? And these are all called as an edges, and with the edges we are connecting each and every statement like this, and we are showing that how the flow of control can be done from statement to statement. Is it clear? This can be called it as an control flow graph. Control flow graph. And what the variations of the control flow graphs? Here, usually we don't include the declarations. Just by example, int x semicolon. These type of declarations are not included here in control flow graphs. CFG is not in context-free grammar. Here, it is in control flow graphs. And these may not want a unique entry and this may want a unique entry and exit point. What it means is the flow graph, in the flow graph representations, compulsory we need to use the two nodes. What the two nodes are, entry node and the exit node. In between the flow of control. In between we are showing how the control flow can be done from block to block. And here we can also include the group statements, and we are calling them as a basic block. Again, by recalling what the definition of the basic block is, it is a sequence of consecutive instructions or consecutive statements. And what the condition here for representing the basic block is, with no branches into or out of the block, then only we can say that it is a basic block. The basic block consisting of or containing a sequence of instructions, but does not include branches. It may be into or out of the block. Then we can say that it is a basic block. We can define that it is a basic block. And here in the last previous slides, I explained this with just it is a flow graph from the source of code. And now it is the flow graph with the basic blocks. See here, my basic block B1 consisting of the two statements x is equal to a plus b, y is equal to a into b. And B2 consisting of a statement, a conditional statement y greater than a. And my B3 block consisting of the statements a is equal to a plus 1 and x is equal to a plus b. And this is the first assignment statement. This is the first assignment statement, and that this can be called it as a leader of the leader that is associated with x and y, right? It is a leader block. And this is a representation with the basic block. This is a flow graph representation with basic blocks, and it can lead to more efficient implementations. When you use the control flow graphs with basic blocks, can lead to more efficient implementations and but more complicated to explain, so but we'll use single statement blocks in lectures. Here only we are using the single block statements, and it is the comparison between the control flow graph and the abstract syntax tree. And here we're having some similarities and some differences between the control flow graph and the abstract syntax tree. And what are those ones? Control flow graphs are much similar than abstract syntax trees. And in low forms, in less redundancy, only simple expressions. When we are considering this type of constraints, then the control flow graph are much simpler than the abstract syntax trees. And these abstract syntax trees are more faithful representations when the control flow graphs introduce the temporaries like T1 is equal to T2 is equal to and so on, Tn is equal to like that. And also here we can lose block structure of the programs. So far here, the abstract syntax tree is easier to report the errors and any other messages, and it is easier to explain to the programmers, and it is easy to unphrase to produce the reachable code. And the control flow graph itself, it is having some advantages, and the abstract syntax tree itself is having some advantages. And while comparing to the both, the control flow graph is in some cases it is much simpler than the abstract syntax tree, and in some cases the abstract syntax trees are simpler or easier than the control flow graphs, right? And here, the today's concept in the global optimization, the concept is about the data flow analysis. And here, as I already explained what the data flow analysis is, and what it means is I already explained what the local optimization and global optimization is. And in the global optimization, totally the global optimization takes place based on the usage of data flow analysis. Whatever the optimizations that we are going to apply in global optimizations, those are totally based on the data flow analysis. That means there we are using the data flow analysis. With the data flow analysis, we are implementing this global optimization. And here, again, I'm explaining the two types of global optimizations, and that means there are two types of analysis performed for global optimizations. The first one is a control flow analysis, and the second one is a data flow analysis. And what is the control flow analysis? Because this thing I already explained, the concept of control flow analysis or control flow graphs I already explained in local optimization, and at the starting of this today class also I explained how to represent the control flow graphs and what is a control flow graph and the difference. That means the comparison between the control flow graphs and the abstract syntax trees. And here, what the control flow analysis is, it determines the information regarding the arrangements of graph nodes. Make a note, that is basic blocks. Arrangement of graph nodes means basic blocks. And what it determines the information regarding the arrangement of graph nodes. Those we can call it as a basic nodes. And presence of loops, nesting of loops, and nodes visited before execution of a specific node. All these are all determined by the control flow analysis. And using this analysis optimization, all this can be performed. And here in control flow analysis, the analysis is made on the flow of control just by carefully examining the program flow graph. Just by carefully examining the program flow graph. And while coming to the data flow analysis, this analysis is made on the data flow. Make it clear. And the analysis made on the flow of control is an control flow. The analysis made on the data flow is an data flow analysis. And here, the data flow analysis determines the information regarding the definition and the use of the data. Definition and use of the data. Once recall the concept like an basic block, and after the in the last classes I explained what the definition of the basic block, and there I explained two most important terminologies in basic blocks. What are those? Live and dead, define and use. Right? Live and dead, define and use. And here also regarding the definition and use of the data, what the data flow analysis determines means the information regarding the definition and use of the data in the program, right? And by using this kind of analysis optimization, we can do the data flow analysis in such a manner. And here, this data flow analysis is basically a process in which the values are computed using the data flow properties. Make it clear. Here, by using the data flow properties, we are computing the values. That's why finally how we're defining this data flow analysis is basically a process in which the values are computed using the data flow properties. And here, this data flow analysis is a framework for proving some facts about the program. And how to prove that facts means just by computing the values, we can prove that facts. Or just by using the data flow analysis equations, we can prove that to the facts of the about the program. And here we're having some reasons about lots of little facts, and there is some interaction between there is no interaction between the facts, like works based on properties about how program computes. That's what we're going to learn here. And based on all the paths throughout the program, here we're including the infeasible paths also. With including the infeasible paths throughout the program, the optimization is applicable because it is a global optimization, right? And what are the properties? Data flow properties means here this is the first data flow property. See the name of it. The data flow property represents the certain information regarding the usefulness of the data items. The certain information regarding the usefulness of the data items for the purpose of optimization. And here the data flow, so we are having some of the data flow properties. With the data flow properties, we are implementing this data flow analysis. And the first data flow property is an available expression. And see here, what the available expression is. The expression is denoted by the letter E. E is equal to X of Y. It is an expression, and it is when it is available at a program in a point P, if and only if we are having some conditions. When the conditions satisfied, then only the expression is available, right? And up to now we know how, when we can say that it is a live variable, and when we can say that it is a dead variable, or when we can say that it is a dead unreachable code, or it is unreachable code. All these optimizations we learned up to now, but in this class, in the data flow analysis, the property of the data flow analysis is an available expression. And here we are learning about when the expressions are available at a program. And when the expressions are available, if we are having an expression like it is in the form of a 3-address code representation, E is equal to X of Y. If we are having the expression like E is equal to X of Y, and is available at a program some point P, if and only if along all paths are reaching to point P. Is it clear? And here we need to satisfy the two conditions to show that the expression is available. What the two conditions is? One is on every path from entry node to the exit node. From entry node to the exit node. At the entry node of the graph to the node P, and here the expression is computed at least once. The expression is computed at least once. That means we're having an expression like X of Y, right? The expression X of Y is said to be available at its equivalent point. And what the second thing, what the second constraint is, if it is satisfied, then only we can say that it is the expression is available, right? Available at a program in a point P. And what the second expression is, for the same expression x of y, that is here we are taking just assuming that it is an x plus y. I am using an operator like an addition operator, and it is said to be available when if there are no definitions of x or y, since the most recent occurrence of e is on the path, then only I can say that it is an available expression, right? If the two conditions satisfies, then the expression is available at a program in a point P. And how the optimization takes place here, the optimization is performed, is applied to the available expressions, then what we get means if an expression is available, it need not be recomputed. If the expression is available, it need not be recomputed, at least if it is a register. If it is in a register also, there is no need to recompute the expression, right? Somewhere, not here and there, somewhere if it is in a register, if the expression is in a register means there is no need to compute the expression. Then finally we can say that the expression like e is equal to x of y is available expression. Is it clear? And next, what the data flow facts are here. Is the expression E available? Here from the source code, this is the control flow graph, right? From the control flow graph, here I am applying the property like an available expression property from the data flow analysis. I am applying this property to the source code. And my input is in the form of an control flow graph. And now I am performing the operations of my data analysis on the control flow graph. And here I am showing that his expression is available and which expressions are available. I am defining the facts here. See, x is equal to a plus z is there, y is equal to n into b is there, and y is greater than a is equal to a plus 1, x is equal to a plus b. And here I am having 5 blocks, right? In these 5 blocks, a plus b is available, a into b is available, a plus 1 is available. And how can I say that these 3 expressions are available? Just these two, when these two conditions are satisfied, then I can say that these 3 expressions from the source code are available. Is it clear? And here we're having an generation and kill functions for computing the values, but here we're not going in detail of the computations. That is, here I'm not expanding in detail of the implementation, just I'm showing how the generation and kill table was represented. That means by taking the statements like x is equal to a plus b, here I defined the facts, right? What is the fact? It is in data flow facts. And for these facts, I'm showing that what is the effect of each statement on the set of facts, and when what it is going to be generated and what the statement is going to be killed. And here x is equal to a plus b. Here I'm generating a plus b, and y is equal to a into b. Here I'm generating a into b. If I'm having a statement like a is equal to a plus 1, and for such a statement I'm killing a plus b, a into b, and a plus 1, right? And with the generation function, I defined which statements are generated, and with the kill function, I defined which statements are killed. And this is the computing available expressions. And finally, it can be represented like this. Once see all of you. Initially, it is 5 because x is equal to a plus b. We didn't compute anything, and initially it is 5. And then after performing the statement like an x is equal to a plus b, because it generates an a plus b, by using a generation function, here we generated an a plus b, and that output is given to the y is equal to a into b, and there also we are generating a plus b with a into b statements, and then it is given to the conditional statement like while y greater than a, and then here we are getting a plus b into a into b, the same thing that we are generating here, the same statements we are going to generate here, nothing difference. But at a is equal to a plus 1, it was killed statement, right? So this a plus b and a into b is given to the next control flow data, that is a is equal to a plus 1, then it is 5 because it is in killed, right? So no statement is there to compute. So it is a null. So it is a 5. And then now x is equal to a plus b, and here we are generating an a plus b. Is it clear? And how we compute these means, these are the computing available expressions. How we compute these means, we implement the generation function and the kill function. We are having some data flow equations for the generation function and the kill function. With the implementation of that, we compute these, and we are showing how the computation of the available expressions takes place. And finally, the control flow graph looks like this. After applying a property of an available expression from the data flow analysis, finally the control flow graph shows like this. This is the final control flow graph. Because here we're using the loop, right? We're using the loop because if with condition, if we execute the statement x is equal to a plus b, then it will go to 3. What the 3 is, it is in block 3. What the 3 is, again we need to check for the condition y is greater than u. Again here we are forming the loop. We are forming the loop. So here only we are generating the a plus b, a plus b, and a plus b. And here we're having the most important terminologies like in join point. And what the definition of the join point is, it is a program point. And here when we meet two branches, if in the program or when we are constructing or representing the flow graph, if any two branches meet, then we can say that it is a join point. And here the other terminologies in the available expressions are forward and must problem. And what the forward means, the data flow from in or into out, then we can say that it is a forward expression. And when we can say that it is a must problem expression means we must hold what the property is here. It is an available expression property. At join point, the property must hold on all the paths that are joined. Then only we can say that it is a must problem. And these are the data flow equations we are having. With these equations, we are performing the computations of each and every property in the data flow analysis. And then we are implementing the global optimization. And S be the statement here. And what the success of S is, immediate successor statement of S. And what the predecessor, PRED is nothing but a predecessor. Predecessor of S is immediate predecessor of statement of S. In and out are the input and outputs. We already know that. And in is nothing but a program point just before executing S. Out is nothing but a program point just after executing the S. Right? These are the, we are calling these all are as an transfer functions. And here we are having the equation for the in statement, and we are having the equation for the out statement. By computing these two statements only, we are getting the values, and those values are shown like this. Is it clear now? And these are the data flow equations. And what the next is liveness analysis. This liveness analysis can also be called as in live variables. We all know what the live variable and what the dead variable is. And again, I am explaining about the live variables. And when a variable is live, or when a variable x is live at some point p, if there is a path from p to exit, if there is a path from p to exit, along which the value of x is used before it is redefined, then we can say that it is a live variable. Otherwise, it is said that it is an dead at that point. Is it clear? And here we're having an advantage of this available expressions. What the advantage is here? The use of this available expressions is to eliminate the common sub-expressions, where the common sub-expressions is one of the transformation technique in principal sources of optimization. So this is one advantage here. While we are computing the available expressions, the use of this available expressions is to eliminate the common sub-expressions. And while coming to the liveness, and here we're having some advantages, liveness analysis, and we know which variable is in live and which variable is in dead, right? So when we can say that it is a live variable and it is a dead variable means a variable x is live at some point p when if there is a path from P to the exit, that means we're having an entry and exit when we're representing the flow graphs, right? There is a path from P to the exit along which the value, we're computing the value, we're knowing the value for the X, right? So along which the value of X is used before it is redefined. Before it is redefined, then only we can say that it is an live. Otherwise, it is said to be dead at that point. And what the advantages of using this liveness analysis or live variables means, here we're having two advantages. One is by using these live variables are useful in register allocations, and also these are useful for dead code elimination. This dead code elimination is also another type of a transformation technique from the principal sources of optimization. This is one type of an transformation from the principal sources of optimization. So these are the two most important advantages of liveness analysis. And when we are performing or when we are applying the optimization with this property, and how the output is. If a variable is not live, then no need to keep it in a register. Make it clear. If a variable is not live, no need to keep it in a register. If a variable is dead at some assignment, can eliminate the assignment. We can eliminate that assignment. So here we're only talking about live and dead, right? Variable when the variable is not live, no need to keep it. Keep it in a registers, because from here onwards we're talking about in machine dependent optimizations, right? Only to keep it in a registers. Or if it is in dead, if a variable is dead at assignment statements, can eliminate that assignment statement. And here we're having the data flow equations. And with these data flow equations, we're performing the computations of each and every property for the data flow analysis. And up to now, I explained about the two properties. One is an available expression and another one is an liveness. And here in the available expression, it is a forward must analysis, and it is in liveness, it is a backward may problem. And when it is forward must analysis in available expression, the data flow propagate in same direction as the control flow graph's edges. And here the expressions are available if it is available on all paths. When the expression is available, if it available on all paths, then finally the expression is available. And these are the two constraints that are under a forward must analysis. And when it is in backward may problem, to know if variable is live, need to look at future use, or else if variables is live if available on some path, right? These are the two constraints under the liveness is a backward may problem. And these are the two most important things. One is an forward must and another one is an backward may. Both are the two important properties of the data flow analysis. And here with the generation out still statements, here we're calculating or we're performing the computations. That means in global optimization with these equations, we're implementing the data flow analysis. That means by computing this, we can get the values. And by the values, we can say that which is defined and which is used. And here also we are having the generation and kill functions. And for the same example, here I am talking about the liveness analysis, right? So this is example for the liveness analysis. And what is the effect of each statement on the set of facts? The same statements I'm taking here, but see the difference between the available expression table representation and the liveness analysis. There, once I'm going back, see here, here I am taking the statements like a plus b, a star b, a plus 1. And here I show which statements are generated, that means which expressions are available and which expressions are not available. That means which expressions are generated and which expressions are killed. And here I'm talking about at liveness analysis, I'm talking about the variables, right? There I talk about the expressions, here I'm talking about the variables, right? So I'm taking all the statements along with my conditional statement. I'm taking all the statements here. Here, the both A and B generates because both are the live variables. Here also both are live variables. And here we're not generating anything, but we're forming or showing the condition that if while y is greater than a, that's where here it generates a comma y, and computing the variable a, and also we're assigning to the same variable, so here we're using the a, and here these two are used and we define x, these two are used and we define y, and here nothing is done, nothing computation is done, just we comparing whether y is greater than a or not. If you know the values of y and a, then only we can see the condition whether it is a success or failure. And then here with the computation, here we are using only the variable a with the number constant 1, then the, the value is defined with the a, right? So the a, b, y all are generated variables, and x, y, and a are the killed variables, right? And see, this is the computing layer variables. After performing the computation by using the equations, then we get this. Then we get this, right? See, here when I compute the statement x is equal to a plus b, here I am getting a and b. By giving the values a and b, I am getting x, right? I am defining the x by computing a and b, just by giving an inputs of a and b. And here I know what the value of x, I know what the value of a, I know what the value of b. So x, a, b. And by using this, again I'm computing a and b. Here I'm getting y. See, here I'm getting, up to here I know x, y, a, b, right? And with this only I'm performing the condition with only y, because if I know the value of y and a, then I can check the condition. So y, a, b. And I'm defining a. If I know a, then I can get the value for the a. See, because whatever the thing I'm having here, that was generated here and here also. With the value of y, I computed this, and now with x, a, b, and y, here the computation takes place. And finally, it was totally depending on the x. Finally, depends on the x. So here we're computing the x. Right? Is it clear? And these we can call it as a live variables. If it is an expression, we can take it as an a plus b. Here we're talking about the variables, right? So a comma b. The representation is a comma b, x comma a comma b, x comma y comma a comma b, like that we need to represent. Is it clear? This is an flow. This is an flow graph. Entry and exit is there. In between, with the while condition, we are forming the loop. We are forming an inner loop, right? So this is an computation of computing of the live variables. Is it clear, all of you? And we're having other two more properties of this data flow analysis. What are those? Means reaching definitions and busy expressions. These are the two most important data flow properties in data flow analysis. And in the next class, I will explain the remaining two data flow properties. And I think you all understand the today's session, and starting with what the global optimization is, and just recalling what the local optimization and what the global optimization, and then I explain you what the a conceptual view of this global optimization from the source to abstract syntax tree, and from the tree to control flow graph, and from the control flow to object code. And then about data flow analysis. And here we're having two types, right? Two types of data flow analysis in global, two types of global optimizations. One is in control flow analysis, and the another one is in data flow analysis. And the control flow analysis is totally about the control flow graphs. And I already discussed about this control flow graphs in the last classes, and the starting of this today's session also. Just I recalled what the flow graph is and how to represent the flow graph. And then about the data flow analysis. And finally, entering into the properties of data flow analysis, starting with the available expressions, and then the second, and knowing what the available expressions is, what the conditions that are need to satisfy to show that the expression is an available, and what the terminologies that are under the available expressions and how to compute the available expressions. And then the next one is a liveness analysis that we can also call as a live variables. And there are different when we can say that it is a live variable and when we can say that it is a dead variable. And also we're having some data flow equations, and I explain those equations. Just I show you the equations. We are not going in depth of those equations because we are not implementing anything here. Just by knowing how the computations takes place, I am showing the equations of the properties. That's it. And finally, I show you how the computing variables are represented. And these are the two important properties of the data flow analysis. And in the next class, I will explain the remaining two data flow analysis properties.